Hello, this is Group 18's Power Consumption Final Project for Engineering 1330, Section 002. This project examines power consumption in Tetuan City using weather data. The goal is to predict power consumption in 3 zones using temperature, humidity, and wind speed. The goal is to create models that can predict power consumption in 3 different zones and compare which model worked best. First, I loaded the dataset into Python and cleaned the column names to make the data easier to use. I then selected the numerical variables needed for the project. The input for the models were temperature, humidity, and wind speed, and the outputs were the power consumption values for Zone 1, Zone 2, and Zone 3. Next, I explored the data using graphs and visualizations. I used scatter plots and scatter matrix graphs to look at the relationships between the variables. From the graphs, I noticed that temperature and humidity seem to affect power consumption more than wind speed.
For this part of the project, I created 3 different models for each zone: a linear regression model, a polynomial regression model, and a decision tree regression model. These graphs compare the actual power consumption values to the predicted values from each model. The x-axis shows the actual power consumption and the y-axis shows the predicted power consumption. The red dashed line represents a perfect prediction, so the closer the points are to that red line, the better the model is performing. For Zone 1, the linear and polynomial models are fairly close to each other, but the polynomial model performs slightly better. The decision tree model is more spread out, which means it is less accurate for this data. For Zone 2, the predictions are also spread out and the model performance is weaker compared to the other zones. The points are not as close to the red line, which means the model has more prediction error. For Zone 3, the points show slightly better alignment compared to Zone 1 and 2. This matches the R2 results because Zone 3 had the highest R2 value. That means Zone 3 was the best performing zone overall.
In model evaluation for this section, I evaluated the performance of the models using visualization tools. These graphs compare the actual power consumption values with the predicted values from the models. The x-axis shows the actual power consumption, the y-axis shows the predicted power consumption. If the model was perfect, the points would form a straight diagonal line. Instead, the points are somewhat spread out, which means the model has some prediction error. For Zone 1, the graph shows a moderate relationship between the actual and predicted values. The model captures general trends, but there is still noticeable variation. For Zone 2, the points are more spread out, which means the predictions are less accurate compared to the other zones. For Zone 3, the points appear slightly closer together and more aligned, which matches with the higher R2 values from earlier. This means Zone 3 has the best overall model performance. Overall, the visualizations help confirm the evaluation metrics like MSE, RMSE, and R-squared. The models are able to identify some patterns in power consumptions, but they are not perfect predictors. And predictors for weather conditions. In this section, I tested the trained models using new weather conditions. I entered sample values for temperature, humidity, and wind speed into the model. The program then generated predicted power consumption values for Zone 1, Zone 2, and Zone 3. This demonstrates how the models can be used to estimate future power consumption based on weather data. Even though the predictions are estimates, they show how machine learning models can help analyze energy usage patterns. On to input interference. I created a simple user input interference. This allows the user to manually enter temperature, humidity, and wind speed values. For temperature, I entered 6.559. For humidity, I entered 73.8. For wind speed, I entered 0.003. This gave us all 3 predicted power consumptions for Zone 1, Zone 2, and Zone 3. This makes the project more interactive because the user can test different weather conditions and immediately see predicted outputs. To add observation interference, I also created this allows users to enter a completely new observation into the dataset, including weather conditions and power consumption values for all 3 zones. Once the information is entered, the new row is added to the dataset successfully. This feature helps make the project more flexible because the dataset can continue growing with additional data. In conclusion, this project used weather data to predict power consumption in 3 zones in Tutuan City. Temperature, humidity, and wind speeds were used as input variables, and multiple machine learning models were tested. The results showed that weather variables do affect power consumption, although the models still have some prediction error. Out of the 3 zones, Zone 3 performed the best based on the evaluation metrics and visualizations. Overall, this project demonstrated how machine learning and data analysis can be used to study energy consumption and make future predictions. That concludes this presentation.